Hello and welcome to our next set of college algebra notes. We're on Unit 3, Outcomes 6. Again, pretty close to the end. This is our last set of notes. We're going to be dealing with exponential functions and logarithmic functions. The last two sections we have left after this, we're going to change up and do something kind of different. So here we get to finish off those exponential and logarithmic functions. Like I mentioned in the last set of notes, this section is going to be dealing with applications. So we're going to look at some real life uses of exponential functions. We'll focus mostly on exponential functions because those are most likely what you'll see in the future. So first off, we just want to talk about how we can describe exponential growth and decay. Model this with exponential functions. We usually either write as f of t equals a sub 0 e to the kt or a equals a sub 0 to the kt. We just use the f of t version if you want to remind everybody this is a function. A lot of times people just use this a version where a is the final amount. A sub 0 is just a way of denoting the starting amount. So we use a for an amount, and then the sub 0 just means that time 0 at the beginning. So that's the starting amount. The k here is called the constant of growth, so the growth rate. It is a number that will just describe how quickly this exponential growth is happening. The number will depend on the situation. So we'll use this model for all kinds of things. We use it for the population of a bunny or the population of a virus, or we'll use it for radioactive decay for different elements. And so the k will change depending on what you're studying. So if you're studying one population of bunnies, k will be a different one number, but if you study a virus, you're going to get a different number. Radioactive elements will have different k's. Each element will have its own growth rate or decay rate. T here will be your time. So we're going to be using this formula. It's used for both exponential growth and decay. If k is positive, if it's bigger than 0, then we're actually doing a growing entity. So every time you have exponential growth, it's because your growth rate, k, is a positive number, so things are going to get bigger and bigger. The power is positive, so it's going to get bigger over time. It's going to be a positive exponential function, one that goes up to the right and increasing exponential function. So that would be, this function right here would be a growing function because the growth rate is bigger than 0, increasing. If, however, k is less than 0, so you have a negative growth rate, well, now it's a decay rate. It's actually something that is going smaller over time. This is what you'll see with radioactive elements, because over time they become less and less and give off their radiation, and so then there's less radiation to give off over time. And so these will be decaying if the k is less than 0, and that's what happens if you have a decay rate, if you have something that's decreasing over time. It'll start off, it'll decrease quickly, but over time it'll actually level off and it'll stick around for a long time because at the end bottom it kind of levels off. Versus like the growth where it starts off not growing very quickly, but over time it grows faster and faster and faster. First thing you should be able to do is you should be able to identify which functions actually are growing populations. If I'm looking for a growing population, I'm really just looking for the k, the growth rate, to be positive. So that means that this is our growing rate, right? Here we have 0.05, so k is 0.05, which is bigger than 0. It's positive, and so this is a growth rate. Nothing else matters. You're really just looking for that power, the number in front of the time, that growth rate to be positive. Versus this other one here, this negative 5.02 is negative, so k here is negative 5.02, which is less than 0. It's negative, so this is a decay rate. It's actually decreasing over time. Again, the first number here on both of these actually tells you how much you start with. So this one actually starts with more. It starts with 400 at the time 0. This one starts with 240 at the time 0. But this one's going to decrease over time. So 400 is the most you're going to have, and it's going to decrease. This one, 240, is the least you're going to have because you start with 240, and then it's going to grow over time. It's going to get higher. So you should be able to recognize that when you look at one of these exponential functions. Look at that growth rate and tell whether it's a positive or negative, and know that a positive means it's increasing, going up to the right, and negative means it's decreasing, going down to the right. Okay, I got a story problem. I live in Box Elder. Across the creek from where I live, there's like 3 different horse barns. It means that during the summer we get a lot of flies, so I have a little problem about that. So your professor can't remember which of the following equations will model the population A in millions. So we're looking at the total population in millions of flies. T days after June 15th, times would be the days after June 15th, and the horse barn across the creek from his house. One of the 3. There's 3 of them over there. He believes it's the equation with the greatest growth rate. There's a lot of flies, so I'm going to go with the biggest growth rate. Select the appropriate equation used to determine the percentage of growth the fly population has each day and find the number of flies on June 25th. So we want the greatest growth rate, right? So we're looking for the equation with the greatest growth rate. So if we look at the equations here, first off, we know that this second equation is no good because that one is decay. You can see here it's got a negative 0.5, so this one's decayed, so we definitely don't want that one. So look at the other here, I have 0.01, 0.00, 0.04, so it's actually the bottom one. This is the one we're looking for because 0.045 is the largest number here for growth rate. Since that's the largest, 0.045 beats out the 0.005 and the 0.019. That one's the equation we're going to use. So we're going to use this equation, and we want to find the number of flies on June 25th, which is my anniversary. It's already past this summer, but June 25th is my anniversary. To do this, first off, we got to figure out what the time is for June 25th. Well, the time is t days after June 15th. So we just got to figure out how much time has passed. So if I take the 25th minus the 15th, the starting point, we see that 10 days have passed, so time is 10. We can just put that in our equation. So the amount of flies on my anniversary is going to be 48 times e to the 0.045 times 10. And this one, since we know the time, we're just looking for the final amount, we can just plug the time in to get an answer. We don't have to do much solving here. We just got to plug this in here. So we're going to do 48 times second e. Remember that there's the e button down here. That's your e button. I have to hit the second button to make it do e instead of the ln. So e. When you're doing this, it's always good to put parentheses if you have multiplication to do in the power. So we're going to put 0.045 times 10. You could just multiply those first in your head. That's fine. If you know that gives you 0.45 instead of 0.045 times 10. But if you don't multiply them in your head, it's a good idea to put parentheses around them like that. Hit enter, and we see that there are 75 million flies, right? Because we said this is in millions. So the final amount is going to be 75.28, and then again, that's millions of flies. So lots of flies, right? Started off with 48, now we're at 75. That's only in 10 days. Thankfully, flies don't really grow, exponentially constantly because there's things like birds eating them and stuff like that. But if they did, they'd cover up the world pretty fast because exponential growth is a really fast type of growth. Okay, now one more part to this question. The last part here says, determine how long it will take for the population of the flies to double. So we're going to do this. We're going to figure out how long it takes to double. That means that the final amount, A, is going to be twice the starting amount, A sub 0. In this case, in this problem, we can actually figure out what that final amount is. We can just say, oh yeah, the first amount is 48. A sub 0 is 48. So we can say that the final amount, A, is just going to be twice that. So A is 2 times 48, or 96. So you have the number you're starting with. If you know the number is 48 and start with, you can do this. And then you can write your equation with the final amount being 96 and the starting amount being 48, e to the 0.045 t, and solve for t. But you'll notice the first thing you're going to do on a problem like this, when you solve like this, is before you can work on this power with the t inside, first thing you do is you're trying to get rid of this 48 because it's extra stuff on this side. So to undo this multiplication, you divide by 48 on both sides. That's one of the first steps when we're solving these equations with powers. So you always want to get the part with the power by itself first. So I'm going to get rid of that 48 on this side, and you'll see what happens is on this left side you get 96 divided by 48, which is 2. So we end up with 2 e to the 0.045 t. And this is always going to happen when you're doing a doubling problem. Because what are you trying to do? You're trying to double. So you want to have twice as much. You need a 2 over here. So you can actually kind of almost ignore this step where I put 96 on this side and 48 on this side. You can just get rid of those two numbers and say 2 equals the e part because you're looking to double. You want to take this amount and have it be twice your initial amount to get your final answer. So if you want to, you can kind of bypass this step. You can just say, okay, if I'm doing a doubling problem, well, then I'm just going to take the e part and set it equal to 2 because I want to double. I want this to be twice as much as what I started with. I want to double. So if I do 2 times this, I get my final amount. So you can kind of bypass this step. You don't have to because this definitely worked to get us the 2 this way as well. But that's just something to point out. When you're thinking about doubling, you're always going to end up with a 2 on this side equals your exponential part, your e part. Now, with these, because it does have e for a base, the way to get rid of this e and get this t out of the power is to take the natural log of both sides. And we'll see that a lot today. We're going to do the natural log of both sides a ton because we're going to have a lot of problems with e's in them. And even if they don't have an e, that's usually the go-to method. So take natural log, so I have natural log of 2 equals natural log of e to the 0.045 t. And again, the point of this is the natural log and the e do cancel. So we're just left with natural log of 2 equals 0.045 t. Last step here, we're going to try and solve for t, so we're going to divide both sides to undo this multiplication. We're going to divide by 0.045. 0.045 on both sides, which cancels this right here. So t is whatever we get when you type in natural log of 2 divided by 0.045. And because this is an application story problem section, we're definitely going to want just the actual decimal answers for this. We're not going to leave it like this because that's not very nice when you're trying to tell people how much time it's going to take. You're going to want to actually type this in. So natural log of 2, close that, divide it by 0.045, and that's our answer. So our answer is 15.4. So we get 15.4 for the time. So the time, again, remember the time is the number of days after June 15th. So it's going to take 15.4 days, or it's going to happen on June 30th. It'll be halfway through the day. You know, actually probably almost halfway through June 31st. But so somewhere between the 30th and 31st. But they were just asking for how long, so we don't have to worry about the exact date. But we'll know that towards the end of the month. I hope there's 30 days in June. Oh, there's only 30. July 1st. All right. So that's the idea. So we're using this exponential function. If they give you the time, you can just put it in and get the result out. If they don't give you the time, if they ask for the time, that's where we're going to have to use our logs, our natural log of both sides, to solve and find the time. Again, if you're doing a doubling problem, which you'll see a few doubling problems in the homework and stuff, remember that with doubling, you just want this e part to equal 2, because that will double. So we'll see that happen. I'll do it again in the notes here. Let's do a couple more problems using the exponential growth decay. This time we'll do one that deals with decay. So this is a radioactive decay problem. So let's just read this real quick. Strontium-90 is a waste product from nuclear reactors. As a consequence of fallout from atmospheric nuclear tests, we all have a measurable amount of strontium-90 in our bones. So did you know that? You're actually radioactive. Everybody is. It's measurable. It's not huge, right? That's why we're not all dying. But you actually do have some radioactive elements in your bones. That's part of everybody. The half-life of strontium-90 is 28 years, which means that after 28 years, half of your given amount will have decayed away. So if you start out and you have 10 pounds of strontium-90, and that's what you have to start with, then after 28 years, 5 pounds of that will become inert, give off its radioactivity, and it will stop being radioactive. The other 5 pounds will still be radioactive. And that works for 10 pounds, but also works for 1 pound. If you start off with 1 pound, after 28 years, you'll have half a pound that's still radioactive. So what you hopefully saw there is that it doesn't matter how much you start with. After 28 years, you always have half as much, which is why they call that the half-life. And that when you have a bigger amount, it's going to decay a lot faster, right? Because you saw how we had 10 pounds and we lost 5 pounds in 28 years. But if you only have 1 pound, you only lose half a pound in 28 years. So actually the dissipation becomes slower and slower over time, so you're losing less and less. Still within the same 28 years, but since you have less to start with, you'll lose less over those 28 years. Okay. If only 12% of the dispersed amount of strontium-90 is observed, how long has it been since the initial dispersal? So they taught us that they had 12% of the dispersed amount is left, and they want the time, how long, since the initial dispersal. So there's only 12% left. When did it start? So they're giving us here that the final amount, A, is going to be 12%, or 0.12, of the starting amount, A sub 0. So they want us to solve this equation. Now we're still going to be using that A equals A sub 0 e to the kt, because we're trying to do radioactive decay, and so this is the formula for radioactive decay. And you can see how we have that kind of same thing as the doubling, where we have A and A sub 0, so we can work with that. The problem here is they want us to find time, and they never told us what the K is. Now I get some students that look and say, well, what isn't the 28 years decay? Well, no, 28 years is a time, but it's not this time, right? Because we want to know how long to get 12%, not half. And K is actually a growth rate, so it's going to be like a rate per year. So what they did is they actually gave us enough information to find K ourselves, but they didn't give us K. And they do this a lot with radioactive elements. They give you the half-life, because that's pretty commonly known information. It's published all over the place. You can just Google half-lives for different elements. And then they expect you to use the half-life. So we're going to kind of come back to this later. We're going to use the half-life to find K. So what we're going to do is we're going to think about the fact that with strontium-90, after 28 years, you're going to have half as much. It's not going to double, it's going to be half. So we know that if the time is 28, then the final amount is going to be half the starting amount. Now you could pick a number here, and this is what I've done in the past. I'll start off with like 10 pounds as my starting amount, and then my half will be like 5 pounds. What ends up happening is you always end up dividing across, and you end up with 1/2 equal to the E part. So just like with doubling, we have 2 equals to it. With halving, we end up with 1/2 equals the E part. So we're going to have E to the K, and this time we're going to do T as 28, because 28 is how come we have half-life of, the half of the amount. So 28. So if you're doing a half-life, you can always just put 1/2 on this side and then just grab the E part. Because we know that when you divide the A sub 0 across, since this much is going to be the starting amount, and that's going to be the final amount, which is half as much, you always divide and get 1/2. So like if I pick this one to be 10 and that one's 5, because the final amount's half as much, 10, 5 divided by 10 gives us 1/2. So this is always what you're going to see with half-life. When you do half-life, it's going to be 1/2. You have half as much equals just the E part. Now this equation, the only thing we're missing is K. Remember, E is a number. It's actually a number in your calculator. So you have to worry about it. We're just looking for K, and then that will know what the growth rate is. So we're finding the growth rate first before we actually solve the problem. So we started out thinking about this and said, well, you can't solve that yet, so we're going to find K first. So to find this, we're going to take the natural log of both sides, because that's how we get rid of this E and kind of get the K out of the power here. So we're going to do natural log of 1/2 equals natural log of E to the K28. Here, the natural log and the E do cancel. Those guys are gone. So we get natural log of 1/2 equals K times 28. And then we want to solve for K, so we're going to divide both sides by 28. So these guys cancel. So K is whatever you get when you do natural log of 1/2 divided by 28. That's K. Okay, so to divide that out, natural log 1/2 divided by 28, we're going to throw that in our calculator. So we get natural log of 1 divided by 2, so that's 1/2. And then make sure you close the parentheses before you divide by 28. So the growth rate for this K is a negative 0.025, if you want. Notice this is negative, and that's good because we're doing a decay. This is radioactivity where it's decaying, it's going away. And so you should get a negative number. If you get a positive number when you're doing radioactivity, something's wrong, because radioactivity shouldn't get worse over time. It should dissipate over time. There are certain like nuclear reactions where you can have like nuclear leftovers, but most of the time radioactive elements are just slowly dissipating over time. They're not getting bigger, getting more. So this makes sense to get a negative number for this. So we put in there, K is negative 0.024. I'm going to actually go all the way to the 248. More decimals here will just give me a more accurate answer at the end. So that's why I like to do that. Okay, so that gives me K. So now I can go back to my original problem where we said the final amount is going to be 0.12 times the original amount. We're going to have 12% left at the end. And now we can use K that we found, because now we know that K is negative 0.0248. Now the nice thing about this radioactive decay and the K value, the growth decay rate, that does not change. So once you know what the decay rate is for strontium-90, that's always the decay rate for strontium-90. That does not change. So I don't know why people don't publish that instead of the half-life. I think there's probably reasons for that. Half-life is just kind of something we've done for a long time, and uh, advanced mathematician could use the half-life and find K pretty fast. But they could make a table of all the K values for the radioactive elements just as well. It would actually give you, this information pretty straightforward, because once you know what K is, it's stuck. It stays the same. Again, that's for just the strontium-90 though. So if the next problem is dealing with uranium instead of strontium, or strontium-89 instead of strontium-90, as soon as you change that, do a different isotope or a different element, then it's not the same K value. So this is only the K for strontium-90. So now if you do another problem with strontium-90, you know what the K is. Okay, we got K. We know we're doing 12%. We're still working with that original equation. So here, I'm going to go ahead and plug these things in. So just like before, when we were doing doubling or half, you can use this 12% here and say that with this a and this a sub 0, when we divide a sub 0 across and all that, we'll end up with 12%. So the final amount is going to be 12% of the original amount. So we're going to end up with 0.12 on this side equals e to the k, which we just figured out was negative 0.0248 t. So because we're doing 12%, that's why we have 0.12. We're not doubling, we're not halving, we're doing 12% of the original amount. So we want to find out what value for t makes this e part, this part over here, the e part, do 12% of the original amount, because that's what we want to get to. We want the final amount to be equal to 12% of the original amount. Okay, so that's what we're trying to solve for. We want to solve for t here, so again, we're going to take the natural log. You guys catch that we're doing a lot of taking natural log of both sides. That's very true with this section, and it's going to keep holding true. That's kind of the method for this section is to take natural log of both sides. We get natural log of 0.12, natural log of e to the negative 0.0248 t. The natural log and e cancel. Those guys are gone. So just a natural log of 0.12 equals negative 0.0248 t. Okay, now we're trying to solve for t, so we're going to divide both sides by negative 0.0248. 0.0248. This part cancels. So t is whatever that gives us. So whatever natural log of 0.12 over negative 0.0248, whatever that gives us, that's the time. How long does it take to get down to just 12%? So I'm going to type that in. I'm going to do natural log 0.12 is 12%. Close that parentheses off and divide it by negative. Make sure you're using the negative button, not the minus, because this is a negative. Now I'll try to divide by minus 1 to divide by negative 0.0248. Gives us 85.5 years. Because the half-life was in years, we're dealing with years. That would be our time in years. Now, one thing you can do with this half-life is you can kind of make sure that this answer makes sense. You can kind of look at the result you got and say, does that make sense? Is this a realistic answer? If you think about it, the half-life is 28 years. That means that in 28 years, you will have half as much as you started. So if I start with, 100 pounds, after 28 years, I have 50 pounds. I'm looking to get all the way to 12%, so I'm not there yet, so I gotta keep going. So if I do another half-life, another 28 years, instead of 50 pounds, I'll only have 25% or 25%. And so if I do 28 years twice, which is 56 years, I'm still not there. I'm still down to 25%. So you can see 56 years isn't enough. I had to go further. If you do another 28 years, so 3 times 28 years, that's what? 60 plus 24, I think that's like 84 years. That would get you to 12.5%, because that half of 25 pounds would be 12.5 pounds. And so you can see that 12%, which is a little bit less than 12.5%, is actually just a little bit more than those 84 years. So you can see why this answer makes sense. That, oh yeah, it's going to take me a long time, because every 28 years I'm going to have half as much still. So to get down to just 12%, it's going to take a lot longer than that. If this number was above 50%, so if I was like still 60% or 70%, then I'd expect this answer to be less than 28 years. But because this number is so much smaller than 50%, I'm not surprised this is actually a lot more than 28 years. So you have half-life things several times before I can get down to just 12%. Because half of 100 is 50, half of 50 is 25, half of 25 is 12.5. I'm doing half several times, so I have to do that 28 years multiple times on this one. Okay, so this is a big thing you see a lot with radioactive decay and with exponential growth and decay. a lot of times they'll give you a problem. They won't give you the k value explicitly. They don't tell you what k is, but they'll give you enough information to find k for yourself. So by giving you the half-life, they told you what you need to do to find the k yourself. And then we went and went and solved the problem. But you couldn't solve the problem until you knew what k was. And to find k, we use the half-life to say, we're going to have half as much. So just do e to the k times the time, which was the half-life time, and that we were going to solve for k, and then use that k to get our final answer. So we're going to do a similar thing with the next problem, but the difference here is instead of decay, it's going to be a growth problem. This is my bunny problem. There's Bugs Bunny times. We're going to be dealing with bunnies. So a scientist is trying to determine which of two bunny populations is growing faster. He's determined that the species A bunny population, so we'll look at the first one, species A, we'll call the green species. It has an increasing rate of 1.5% per year. So they're adding 1.5% onto their population every year. And then he looks at species B and determines that the species B bunnies doubled in 42 years. So one, he knows the growth rate. One, he knows that they double every 42 years. We want to determine both the growth rate of the first one, of the second one. We're going to find the growth rate of the second one, so we can look at both growth rates, and the doubling time of the first one. So we're going to do both of those things. We're going to look at the growth rate of species B, and we're going to look at the doubling time of species A. And then finally, we'll figure out which species grows faster, so which population is growing faster. Now, we don't really have to do both of these things to figure out which species is growing faster. As soon as you know both growth rates, then you could compare them. Or if you know both doubling times, you can compare them. Whichever one doubles faster is growing faster. But we're just going to do both just for practice, so we can figure out both things. So first off, we want to look at, let's do the species A first. We want to look at the doubling time for species A. So species A doubling. Remember, that means that the final amount A is twice the starting amount. That's what we're looking for. How much time does that take to double? So to do this, we're still going to be using that formula, A equals A sub 0, e to the kt. That's what we're going to be using still. The growth rate we actually are given, right? So this one, they give us the growth rate. This is k. So this time they told us the k is 1.5%. This is in percent. You always make sure that you put those k's in decimal when you use them. So I'm going to turn this into a decimal. So I'm going to move that 2 spots. So it's going to become 0.015. So I move that decimal 2 spots. That's our growth rate. So each year it's going to grow 1.5%. That's our growth rate. And so we're going to plug this in for k. And we know that this a and a sub 0 is just going to give us that doubling thing. So we can write the equation as 2 equals, for the doubling, e to the k, which is 0.015, times t. So again, when you're doubling, you don't have to worry about writing the a and a sub 0 because we know that the final amount is going to be twice the starting amount. So if I divide these across, I just end up dividing getting 2. I want this number to double that number to give us that number. That's why I can just write the equation like this. We're doubling. That's why we're doing this. Okay, so I'm going to solve this for t. So again, I'll take the natural log of both sides. So the natural log of 2 and natural log of e to the 0.015 t. And by doing the natural log, I can cancel that e again. So just get natural log of 2 equals 0.015 t. Now I can divide to get t by itself. So I'm going to divide both sides by 0.015. 0.15. So I can cancel this part. So t is what we're going to get when we do natural log of 2 over 0.015. That's going to get us our answer. So let's find that out. So let's do natural log of 2, close it off, divided by 0.015. It's going to take 46.2 years. So the time is 46.2 years. Oh, excuse me. Okay, so right off the bat here, this is enough to tell us which one's growing faster. Since species B is growing and doubling every 42 years, and this species is doubling every 46 years, now we can already tell that species B is doubling faster, so it is growing faster, right, because it's doubling more quickly. We're going to keep going and do the other problem as well, so we can look at the growth rates and compare those. But if all you needed to know is which one's going faster, Well, of course, this one's only is taking 46 years. This one's only taking 42 years. So the 42 years doubling is going faster. So that's enough to tell us which one's growing faster. We wouldn't have to keep going if that's all you were looking for. We were asked to find both, so we're going to go ahead and do the other one as well. We're going to find the growth rate for species B, because that was what we were asked to find. So for this one, they have the doubling rate, so doubles in 42 years. So that's what we're going to use to do this one. We're going to use the fact that we know how fast it doubles. So we know that the final amount will be twice the starting amount in time equals 42 years. So if you use a time of 42 years, then we can actually figure out what k is, because we know it's going to double. So we use time is 42 years. So we know that we're going to double. So 2 equals e to the k, which is what we don't know, times time, which is 42. So we know in 42 years, the final amount is going to be double the original amount. So we're going to have this whole doubling thing going on again. So anytime we're doing doubling, we just do the e part equal to 2, because we're doubling like this. Okay, to solve this one, you guys know, we're going to take the natural log of both sides. So natural log 2, natural log of e to the 42. I'm going to put 42k because I like to have the number in front. I just switched them around there. Still the natural log and e cancel. Natural log of 2 equals 42k. Last step, get k by itself, so we're going to divide by 42 on both sides. So divide by 42. Cancel this 42 here. So we get k equals natural log of 2 divided by 42. And we'll just type that in our calculator to get the answer. So we'll type that in to get natural log of 2 divided by 42. That gives us 0.0165. So that's a 1.65% growth. And you can see, of course, that is definitely bigger. 1.65% is higher growth rate than the 1.5% of species A. So this is enough to tell us that for sure, and we kind of knew that already from here, but this tells us again that species B grows faster. Not a huge percentage different, right? Only like a 0.15% difference, but that's enough to have them double 4 years faster. In the long run, they'll grow a lot more because they have a faster growth rate, as long as, other things that don't come into play, like predators and stuff. So that's the idea. So if you're doubling, you're doing 2 times the amount. And if you're using the time it takes to double, you're still kind of doubling. So we can see this doubling thing happens a lot, these kind of problems, and you'll see it a lot in the homework and stuff. Okay, last example I'm going to do here, we're going to go back to finance, because we did do some finance examples previously in the semester, but we did all those when we were just looking for the final amount. So we plug a number in for t and find out the final amount. The problem here, we're going to do it a little bit backwards. So you can actually do problems with interest, where instead of looking for how long or how much money you'll have at the end of your investment, you can actually say, how long will it take me to get to a certain amount, which makes a lot of sense. So a lot of times when you're saving up money, you have a goal. So maybe you're saving up for a car or a house or retirement, and you want to hit a certain target. And so you want to know how long is it going to take me to reach that target. So that's what this problem is about, is investing in trying to reach this target at the end. So it says, often you invest in accounts like 401ks, 403bs, IRAs, 529s. These are all things that grow with compound interest. Suppose you plan on investing, so we're going to invest $6,000 in an account. You think we'll get 14% interest. It compounds monthly. How long will it take for the account to grow to 10,000? So what they've given us here, they've given us the starting amount. Remember, that's your P, your principal, your starting amount. They give us the final amount, how much we want to have at the end. That's 10,000. The interest rate, so 0.14 would be our interest rate R. Compounds monthly. Remember, this is how many times it compounds per year. So N would be 12. And they looked for how long will it take. So then we're looking for T. So they gave us everything for this equation except for the time. So we're actually trying to solve and find time. So let's plug the numbers we have in there. So A, final amount is 10,000. Principal, starting amount is 6,000. 1 plus R, which is 0.14, over 12, because that's monthly, to the power of 12 times T, because we don't know what T is. So that's the idea. So when you're doing problems like this one, you plug everything you know in there, and then you have to solve for t. Like the rest of them, this one is a little different because I'm kind of skipping this step, but like the rest of them, to solve this, we're going to take natural log of both sides. Before we can do that, we're always going to try and get this part with the exponent by itself. So the first thing we're going to do here, we're going to actually divide both sides by 6,000. You know, if they'd asked us how long it took to double our money, then you could have done the 2 trick and just put a 2 here and we're not worried about the 10,000, 6,000. But we're not exactly doubling, right? So 6,000, 10,000 is a double. So you'll see we're actually going to have a number on this side that's not doubling because we aren't exactly doubling. This one, you can write 10,000 over 6,000, but you can simplify this. Remember that when you simplify fractions, you can always cross off paired zeros. That's a really nice, easy way to simplify fractions. So you could write this as 10/6. If you really want to simplify it, you can divide those both by 2 and get 5/3. That's going to be the most simplified that fraction gets. So if you want to simplify that fraction to 5/3, you can. Over here, we still have 1 plus 0.14 over 12 to the 12t power. Okay, now just like the other ones, we are going to use the natural log of both sides, but unlike the other ones, we don't have an e base, right? The base here is not e. So this time, we're not going to use that canceling thing. We are going to take natural log, so take natural log of 5/3 and natural log of 1 plus 0.14 over 12, the whole thing to the 12t power. That's what we're taking the natural log of. But instead of using the canceling, we're going to use the fact that you can take this power and pull it out using the power rule. Remember the power rule that says if you have a log, once you have a natural log, you have a log, you can take the power and you can pull it out front. So the natural log of 5/3 stays the same. Now we have this 12t out front, and then there's the natural log left over with the 1 plus 0.14 over 12 inside. I think sometimes they'll have you just go ahead and multiply this out. You do the stuff inside here, 1 plus 0.14 over 12. It just gives you a decimal number. So if you want to, you can just type that in and get that decimal, and that's fine. Maybe make your life a little bit easier. Same thing if you want to type 5/3. The one problem is then you have to round a little bit. I'm just kind of avoiding rounding until the end. Because once I get t by itself, then I'll just shove everything on the calculator all at once. And that kind of saves me from rounding too much. So divide both sides by 12. Give her this 12. Divided by natural log of 1 plus 0.14 over 12, that whole thing. So I want to get rid of that whole thing. 1 plus 0.14 over 12. So I got rid of the 12. I got rid of this natural log part. All I have left is the t. So I get t equals natural log of 5/3 over 12 times natural log 1 plus 0.14 over 12. Now when I type this in my calculator, I want to make sure I type this in correctly. Since there's a big division bar here, you do need a parentheses around the bottom as well, just to make sure that the division bar works correctly. So that's something you'll see when I'm typing this in. Something that's easy mistake to make. I'm going to do natural log 5 divided by 3, that's the top, close it off. Divided by, I'm going to do a parentheses, do 12 times natural log 1 plus 0.14 divided by 12, close that parentheses, and close the parentheses for the bottom, and then that should give me the right answer, which should be 3.67 if you want to round that. So I'll round that to about 3.67. So not quite, a little more than 3.5 years. This is time, so this would be years. If I want to get $10,000 in my account, I'm going to have to wait about a little more than 3.5 years, and that money will grow that rate if I have that nice 14% interest rate. This is how people invest. Of course, in real life, most people invest by making periodic payments that grow also with compound interest. But yeah, that's the reason why you put them in savings accounts like those 401ks and stuff like that, because they don't just sit there, they also earn interest. So they make a lot of money that way. Okay, that's it for this section. So you saw this section, we really didn't see a lot of logs except for using the natural log of both sides to solve these equations. That's really the primary thing we were doing, was solving equations using the natural log. And a lot of them, the e will cancel with the natural log. That's why we like to do it, this being an exception. But that's it for this section. So we are done with exponentials and logs. Our next set of notes, we're going to move on and do something completely different. So I'll see you then.